Mountains, folds, and faults. There are three forces that help us build mountains. First, compression. This is where rock layers are being squeezed inward, squeezed together. It makes the rock layers thicker and shorter. You can see the movement in these arrows. And it occurs at convergent boundaries. Next, we have tension. This is where rock layers are being stretched, pulled apart, as in these arrows. It makes the rock layers thinner and longer until they snap, typically. It occurs at divergent boundaries. And finally, we have shear stress. This is where rock layers are being pushed in two different directions, sliding, moving the way that scissors move, against each other but not crashing towards or pulling apart. Changes the shape of the rocks and often forms at transform boundaries. Motion on rocks can cause them to bend, as in the left picture, and those bends are called folds, or it can make the rock break, such as the picture on the right, creating faults. First, we're going to do folds. You have two types of folds. These are both formed from compression. First, we have an anticline. I know you need to draw this in your paper. Anticline is an upfold. It's where the rocks that were originally horizontal get bent into this A shape. Next, you have a syncline, which is a downfold in rock layers. That's what you see in this image. I usually remember it. I think of an anticline is like the letter A, and a syncline sinks. Synclines sink. They go down in the center. But they are both frequently formed together, and as you see in this animation, they are formed the same way. They are both formed from compression, where the rock is being crunched together as in a convergent boundary. These are some examples. The one on the left is a rock cut through in Maryland, and on the right there is another fold. This one is in Scotland, I believe. The one on the left, you notice it sinks in the middle, so it is a syncline. And the one on the right reminds you of the letter A, so it's an anticline. Mountains, there are four different types of mountains. First, we have the folded mountains. These are formed where two continental plates collide and the rock becomes folded, making those anticlines and synclines. Great examples are the Appalachians and the Himalayas. Then we have dome mountains. These are almost circular, folded mountain caused by when you have magma underneath the ground pushing upward and creating a dome shape. And the Adirondack Mountains in New York are a good example. This is a side view of the Appalachian Mountains, how they formed from compression when North America and Africa collided. And you see the folds, anticline, syncline, anticline, syncline. And then over time they became eroded away, and only the toughest rock ended up producing ridges. And so we have the Appalachian Mountains we know today. Dome mountains, we've got a couple images here that show you how it forms. Igneous lava, magma, pushes its way up to the surface, and instead of breaking through, which would produce a volcano, it instead pushes the surface of the earth up, creating dome mountains, such as the Adirondacks. We also have volcanoes, which we've discovered before, which are where lava is erupting towards the surface. And finally, we've got what we call fault block mountains. These are mountains formed where there's uplift, making the land stretch and crack, producing faults. And these are formed from tension. It's where the area is being stretched apart. Volcanoes include Mount Fuji in Japan and Mauna Kea in Hawaii. And these are some fault block mountains. The land is being pulled apart, tension, as you see in this image on the left. And Sierra Nevadas, this is an example. on the right. Some pieces get pushed up, others fall down to produce the mountains. When you're looking at faults, there are different types of faults, and the first thing you need to do is figure out where the footwall and the hanging wall are. Please draw this into your notes. Anytime you have a crack in the ground, that's called a fault, and it is typically not going to be perfectly vertical. It's going to be slightly sideways, which means that there will always be a section of rock above it, above the fault line, and always be a section of the rock below the fault line. The one above the fault line is called the hanging wall because it hangs above the fault line. The one beneath it is called the footwall because just like your feet, they are underneath your body. The footwall is underneath the fault line. Personally, I also picture this footwall and imagine that this is a shoe. Toes are down here, and here is the top of my ankle. Here's my heel in the bottom right. So if you picture the one that's got the toes as the footwall, little point on the bottom. Once you figure out which one's the footwall and the hanging wall, you can define what type of fault you have. Here in this image, we've got a fault line right here. The footwall, in this case, is the one with the toes. It's the one underneath the fault line. Here's the footwall, and I'm drawing an F there. The other is the hanging wall. It is above the fault line. So when we're looking at a fault, we always define a fault by how the hanging wall is moving. We pretend our feet are on the footwall. We're standing there, like where this house is, and we describe how the hanging wall moves. In this case, the hanging wall fell down in relation to the footwall. It slid down. Is it normal for things to fall down? Yes, they don't fall up, they fall down. Since that's normal, we call it a normal fault. And this is happening because of tensional forces. The ground is being pulled apart, and this allows the hanging wall to slide down along the slanted fault line, just like it's gone down a slide. You start at the top of the slide, you go down to the bottom, you've moved away. So it's tension. And these are some images of tension faults. These are normal faults because in all of these cases, the hanging wall is falling down in relation to the footwall. Now in this image, again, we find the fault line and notice the left is the footwall and the right is the hanging wall in this particular case. In this image, again, our feet are standing on the footwall and we describe how the hanging wall moves. The hanging wall slid up. That's not normal. It's not normal for things to fall up. So we call this a reverse fault. Imagine if we were standing here at this tree, the hanging wall is just flown up and punching us in the eye. It's a result of compressional forces. The ground is being shoved together, and rather than folding, bending, it's broken, and the hanging wall is pushed over top the footwall. And that's what you see in this image. It is a reverse fault formed from compression. Finally, we have a different motion entirely. Here is our fault line. Again, the one with the toes is on the left, the footwall, and the hanging wall, in this case, is on the right. But if we're standing on the footwall and describing the hanging wall, it is neither moving up nor down. It is slid to the side. This is called a strike-slip fault. The movement is horizontal, not up or down, and this is a result of shearing forces. The ground is being sheared or slid sideways, and this is what happened. This is the type of fault that the San Andreas Fault in California is. California is sliding slightly northwest in relation to the rest of North America. And that's what you see in this image. Rather than going up or down, the land is distorted. This road, for instance, is cut in half. And those are your mountains, faults, and folds.